Hello friends, this is ER Patel Path, and here we are going to learn the model analysis in Workbench and how when we any product have their natural frequency and at which frequency it's a break their own shape by its own natural frequency. And first we are going to learn what is a natural frequency. Okay. So the natural frequency is at which system tend to oscillate in the absence of any driving or damping force. In natural frequency, we are not adding any kinds of the force. It's a natural frequency, but it's a natural frequency of the product. Okay. So this is the my aeroplane propeller, and here you can see at which property at which natural frequency 14657 natural frequency it's a break by its own natural frequency. You can see it here, these two blades is meshing. Okay, so how to do this analysis we will learn by step. And the first question is to why we learn this model analysis and why we learn this natural frequency. So this natural frequency is very important to learn in any model design for the any design engineer, because when we are not learn their natural frequency of any product, so it will deleterious for our the product. You watched the shape of the propeller, what kinds of the effect is done at the 146 natural frequency. First, here we are going to add engineering data in which we add the material for our propeller. Here first I am going to add aluminum for our the propeller, aluminum alloy. We press the plus button and it's add material. Then we go for the geometry. Here I will not do, or here will I will not draw any geometric part, because I drew the part in SolidWorks software, and then after I imported part in this ANSYS software. And how to import the part from SolidWorks software to ANSYS, you can learn or you can watch my first video. Import geometry external data. Here we are using the step extension to import the part from any design software to uh, analysis software. Here you can look it. This is our propeller. Then we back. Okay, and model. In the model, we apply the different boundary conditions and the fixed support, and then we will see what kinds of the effect it's occur in the model. It's take a few time. Okay, here also see other design. First we select the material. Okay, which we applied in engineering data. Okay, aluminum alloy. If you want to add the another material, so you have to go to back into the engineering data and open it. Then after you applied the another material, like we apply the PVC material, which is available at the composite material. This is the PVC material, we applied it here, and then we have to update the project is compulsory. If you do not update the project, then you will not find any material at the model at here. Okay, first you cannot see the material at the PVC. Okay, here you only just it shows the aluminum alloy just only. When I update this project, then we will get the material into the model. It will take a few time to update our the model. Okay, the process is done and we will find the PVC material at here. At the propeller you click and you click at this. You find PVC material. Okay, so this process is needed to find or to add the different material. We are not adding the PVC material, it's aluminum, you can see it here. And then we generate the mesh. Okay, it's already generated by this software mesh. Okay, you can also change the sizing of the mesh at here. Advanced, here you can see the use advanced size function. When the arc shape is too complex, this is not that much kinds of the complex shape, but at the too much complex shape you can provide the proximity and curvature for the better analysis, for the better result. And also you can apply the medium and the fine size. You can see it here, the size is too large, this between. Okay, this two line between size is too large. If I add here the fine size, then I apply the generate mesh, so you will see what kinds of the size we will get between the two line. Here there is a no need to apply this one, but to learn I applied it here. Okay, so you can see the size between the two line is reduced when I apply the fine. Okay, but it will take a few time, it will take a more time compared to the course, compared to the course size. Okay, here we apply the fine size. Then we have to go back for the model, and here we have to insert the fixed support, because we are going to watch at what natural frequency it will break. Okay, we are not adding any damping force or any external force to break it. In the model we apply the fixed support at here. Okay, from here we fix it, and then after we watch at what natural frequency it will break. So in analysis setting, maximum mode to find, here we apply the 6, you can apply the 7, 8, 10, 9. Okay, we apply up to the 8 modes, 8 natural frequency, different 8 natural frequency, fix support, and then go for the solution. Before go for the solution, we applied it here the total deformation. Okay, because uh, we will watch at the total deformation at this fixed support, what kinds of the deformation we will find in this blade, this or the blade. It will take a few time according to your CPU memory. Our result is done, and we will see in this you can find your solution information. It's a huge amount of the data you can copy, and then you will use. Okay, the mode, we apply the different 8 modes, so you can see it here 1 2 8 mode and different natural frequency. It shows the period. Okay, so you can find out the huge amounts of the data at here. Then we go for the total deformation at the first mode. We applied it here the 8 mode, so you can hear the total, you can watch in the total deformation for the first mode. We apply the again deformation for the second mode, so you have to change here to second mode. And also you can see it here the 8 different natural frequency of are the propeller. Okay, 8 different frequency we applied it here, 8 different mode. We apply another total deformation for the third natural frequency. We applied it here for the fourth mode. Then we apply for 5, then for 6, then for 7, then for last one 8, and then go for equivalent. Evaluate all results. And also you can see at here the graph generations. Okay, the graph generation you can see it here up to 1 to 8. Okay, 1 to 8 different frequency, different natural frequency. As the result is done, so we watch, and here you press the animation button so you can watch better. You can see it here the deformation, the gap between the two blades is too low, and in our the mesh product you can see between the each blade you can see the huge amount of the gap, but here in the total deformation you cannot see the huge amounts of the gap between the two propeller, between the two blades. Okay, animate, you can see it at the blue region. It is the zero level of deformation, but at the red it available the 110 mm, that means 11 centimeter deformation we can see at this top edge, at this top edge. At our the blue region you can find the huge amounts of the gap between the two blades, but in the red region, when it occurs the red region, you cannot find out that much kinds of the space. At the second deformation you find out the huge amount of the deformation at here, 157 mm deformation, which is higher than the total first deformation. In the third deformation you can find out the less amounts of the deformation at the red region. Okay, but are the product is the safe, because no one blade are meshing with each other. Okay, our blade is safe, but the deformation is too large. So when we applied the material at this tip edge, or when we change the shape of the our blade, so at that time we remove this kind of the deformation at the this natural frequency. At the fourth natural frequency, or the deformation is reduced. Fourth natural frequency is about 600 600 hertz. At the 5 natural frequency, the huge amounts of the deformation we can see it here, 162 mm deformation. Okay, and we can see it here the 5 natural frequency is 600.78 hertz, so also it's a huge amount of frequency. Then at the 6 we find, or we watch at here the less amount of deformation at here for the 6th natural frequency, 601, and for the 7th natural frequency is 601.91 hertz frequency, we find a huge amount of deformation at this blade, and 1, 2, 3, 4, 5, 6, and 7. At the 7 blade, we find the huge amount of deformation at this red region. Okay, at this red region, 173 are the first at the first frequencies 110, and at the seventh 173. Okay, so it's a 60 gap between the first natural frequency, and at the seventh natural frequency, and at the in the total 8 deformation at the 8 natural frequency. We also find out the huge amount of the deformation 173. Okay, you can see it here what kinds of the effect is generated at here in are the propeller. Okay, at this red region we find out the huge amounts of the deformation around the 173 at 602 natural frequency. This is the frame rate. Okay, if you apply the 10 second, then it will occur a very low. Okay, you can see it here in the better manner. At the blue region it's a safe, and at the red region it's occur it available the huge amounts of the deformation at here. But ultimately in the conclusion our design is safe because no one blade is touch with each other, no one blade touch with each other, so our design is into the safe. In the first before starting this solution, uh, we watch uh, we watch two blade is meshing with each other. So at that time I applied, so we can see that one. I close this one, and we will see that the total deformation when the two blade is a strike with each other. Okay, so that design is the failure. Okay, the failure one, and this is the safe design. Okay, I edited this design, and before starting this video, you watched the one design in which the two blade is a strike with each other. I show you the damage of this model. This one, this two blade is meshed and strike with each other, so I edit into the this design. I add the material at here, and I change the little bit shape of this all the blade, and then after I got this safe result. You cannot find out at here any blade meshing with each other. Okay, so thank you so much, and subscribe and share my channel. Thank you.